So, hello everyone to another edition of Symmetry Seminar. Today we have Pavel Putrov from ICTP in Trieste, and he will tell us about non-invertible symmetries and mixed gravitational anomalies.
Okay, yeah, thank you. And yeah, I would like to thank the organizers of this seminar to inviting me to give a talk. So my talk will be based on a recent preprint done together with Juvin Wang. And it's basically about a certain observation that in certain cases, a mixed anomaly between gravity and some global symmetry can be traded off with the non-invertibility of the corresponding charge operators. And the plan of my talk is the following. There will be three parts. So first, I will focus on the case of U1 global symmetry in 4 dimensions, and then I will consider the case of Z4 global symmetry, which contains fermion parity, again in 4 dimensions. And then I will mention, as an example, a standard model with the number of right-handed neutrino not being equal to the number of flavors. Okay. So before I proceed with technical details, let me mention a general idea behind this kind of observation / construction. So the idea is by no means original and has appeared in other works. And so if you have an anomaly of, say, global P-form symmetry in d-dimensional QFT, this means that classically defined extended charge operators of the respective dimension d minus p minus 1 are not completely topological or require some additional non-canonical choice to be unambiguously defined. So there is some pathology with these charge operators. And one can consider modifying these charge operators by putting on top of them some TQFT, which also which you couple in some way to background to the bulk fields. And if this TQFT itself has some anomaly, it can happen this pathology of TQFT cancels out the pathology of our charge operators. And so the together, the stack of them will be a well-defined topological operator. But of course, in order for this TQFT to have some anomaly, it should be non-invertible. So by doing this we'll earn that our new operators will be non-invertible. That's roughly speaking how the trade-off between these kind of anomalies and non-invertibility can go on. And in particular, this this type of construction has appeared in the work by Choi Lam Shao and also Cordova Mori last year, where they consider the case of a BJ type anomaly in 4 dimensions. And there they consider it anomaly mix between U1 global symmetry and either U1 gauge symmetry or SUN gauge symmetry in 4 dimensions.
Sorry, Pavel, just a quick comment. I thought it only works for PSUN, but not SUN.
Yes. So yeah, if you want to get a material anomaly, yes, you're right. You want to consider PSUN. Yes. Yeah.
Okay.
I was not precise here. Well, SUN or SUN divided by some divisor of n in general. Yeah.
Right. That's right.
Thanks. Yeah, I was being imprecise. So in my construction, the construction which I want to describe in this talk is, in a certain sense, is analogous, but with the gauge symmetry being replaced by gravity. And here, we want to consider gravity to be either as background or maybe as a semi-classical, but not as a full quantum gravity. Well, partly because I don't know what is a full quantum gravity, but another reason that in the full quantum gravity, we are not supposed to have any symmetries. So all symmetries should be either somehow broken or anomalous. So yeah, to be on a conservative side, we want to consider gravity as a background or maybe semi-classical. Okay, so let's consider the case of a global U1 symmetry in 4 dimensions. So in general, the anomaly polynomial, in general, the perturbative anomaly can be described in terms of a degree 6 anomaly polynomial, which looks like this. So it's a polynomial in the first Chern class of the corresponding U1 bundle and the first Pendragian class of the tangent bundle. And so if you want to, so we can consider these characteristic classes in Dirac cohomology, and then we can write the standard representatives of them. So the first chain class is just the field strength of the corresponding U1 gauge field divided by 2 pi. And the Pantragian class is a trace of R with R, where R is a curvature 2 form, which is expressed in the following way through the omega, which is a Levi-Civita connection 1 form on the tangent frame bundle, so which is often in the physics literature also known as a spin connection. And so I wrote these the coefficients in the following form in terms of K and L, so that in this form the K and L they can take integer values. Well, to be precise, L is integer if we assume that fermion parity is contained into U1 symmetry. In other words, the U1 is actually spin C. So the U1 global bundle is actually part of a spin C structure. And if the fermion parity is not contained into U1, the L coefficient is actually a multiple of the 1,4 instead, integer multiple of 1,4. Any questions? Okay, so this anomaly polynomial corresponds to a divergence of the U1 current. So it implies that the divergence of the current is non-zero and has the following form. So it's expressed through the first chain class of the U1 bundle and the Pantragian class of the tangent bundle. In particular, if the anomaly is present, the current is not conserved. So let's first consider kind of a simplification. So consider the case when the U1 background is trivial. So we will only care about the effect of kind of mixed U1 and gravitational anomaly. So we will assume that the background U1 gauge field is trivial, and moreover, we assume that our spacetime for manifold M4 is spin. And then the divergence equation simplifies to the following simple form. So we see that here it means that in general curved background, the current is not conserved. And this will imply that the corresponding charge operators are not going to be topological. So if we define the kind of the naive classical charge operators as follows, so the exponentiated integral over star j over y, where y is some three-dimensional support of this operator, which we, so for now, we will assume that this is just some nice submanifold inside the spacetime. And so classically, such operators are labeled by angle alpha. Here is defined modulo 2 pi. And so the way kind of to explicitly see that it's not topological, we consider a small deformation from y to y prime, where kind of a little bit shifted. So the difference between this y and y prime is, so we deform y to a homologous y prime. So the difference is a boundary of a certain 4-chain, or kind of, you can just kind of schematically imagine the following picture. And then the ratio of two operators supported on y and y prime is, by using the Stokes theorem, can be expressed as the integral over divergence of this current over this z, the full volume. And using the fact that the divergence is given the first Pantragian class, we get the following expression. So it's expressed using the integral of the first Pantragian class. So here I'm kind of being kind of a cavalier with my notation. So I kind of I use the same notation for classes, for characteristic classes like C1 and P1, and they kind of representative, particular representative. So here I just understand that P1 is a particular 4-4.
So why did you assume the spin condition on a manifold?
Yes, so here I'm going to assume that, so since I want to assume that the background U1 is trivial, I also want to assume that the four-manifold spin, but later, when we consider turning on the non-trivial background U1, we will be able to relax this condition. But for now, yes, for now, our ambient space is assumed to be spin. Any other questions? Okay, so we can fix kind of, at least naively, we can fix it in the following way. So we can note that the locally, the Pendragon class is given by is a total derivative, namely it's a total derivative of the Chern-Simons, of the gravitational Chern-Simons reform, which expressed in the following way through the spin connection one form omega. And then, so we basically can consider shifting our current by the star of our current by this three form with appropriate coefficient. So that, in other words, we modify our charge operator by exponential of integral over this gravitational Chern-Simons reform over the same three manifold Y which we had before. And again, it's equivalent just to kind of shifting, shifting the current by the gravitational Chern-Simons. And since, so we can kind of consider this ratio of the new operators again and again. So we will use a Stokes theorem you can use a Stokes theorem to see that the the difference between integrals of the Chern-Simons reform over Y and Y prime will be given by the integral of the first Pendragon class over this four volume, and this integral exactly will cancel the integral of pi 1 which we had before. So the ratio of the new modified operators will be 1. So they will be invariant under small deformations. However, when we introduce omega as a spin connection and Chern-Simons, gravitational Chern-Simons in particular, we have to make a choice of the 4D wirebind. So we have to, in other words, it's a choice of trivialization of the tangent bundle. So we have to choose our basis vectors, so orthonormal basis on the tangent space, each point of the tangent space. And so since we're only interested in integrating this Chern-Simons functional in some neighborhood, in Y and maybe some kind of neighborhood, so we only need to define this Chern-Simons three form in the neighborhood of Y, because we only need to integrate Chern-Simons three form over Y and maybe consider some deformations, some small deformations. So it's we can choose, there is a natural choice of this 4D variable, which consists of choosing the framing on our three manifold Y and adding to it a normal vector. We choose a kind of a well bind in the three manifold, which I think sometimes called a dry bind. There are three dimensions, and we supplement it with a normal unit vector. However, in general, there is no canonical choice of the framing on a three manifold, and that's a problem. So we have some ambiguity actually how we define such operators. So in particular, we can change of framing. We can consider change of framing corresponding to a kind of large SO3 gauge transformation, because our the frame bundle over three manifold can be considered as a SO3 principal bundle. So we consider the change of framing or the change of this wheel bind as a SO3 as a SO3 gauge transformation. So we know that the Chern-Simons function is invariant under small gauge transformation, but it's not necessarily invariant under large gauge transformations. The large gauge transformations are classified by this pi 3 of the gauge group, which is Z in this case. So we can consider a large gauge transformation corresponding to a particular integer f, and it will shift the integral over Chern-Simons three form of Y by this 2 pi times this integer, and this means that the operator will shift by the corresponding, will be multiplied by the corresponding phase. So let me make a quick kind of technical remark. So we talked about the choice of framing, but actually, as was shown by Tia, this integral of transformance function actually depends on what is called two framings. It's a slightly less information. So it's a trivialization. One way to understand is the trivialization of the two copies of the tangent bundle, or equivalently, this can be also a choice of P1 structure, which means a trivialization of the P1 plus. So the frame is the kind of the complete framing choice is also involves a trivialization of W2, the second Stiefel-Witten class, which correspond to a choice of spin structure. But in here, we don't need we don't have a dependence on the trivialization of W2. We only have a dependence on the trivialization of P1. Okay, this was just some technical remark.
Sorry, Pavel, about the two framing, does that mean if you choose a different tangential structure? Okay, so there's a canonical two framing for every oriented three manifold. So does that mean if I choose a different tangential structure, then I don't have to worry about this 2 pi f large gauge transformation?
I'm not sure what you mean by canonical framing. So if you have a considered closed three manifold, yeah, there is a way to define a canonical framing, which two framing, which was given by, but this choice is not a local choice. So, for example, if you want to have a kind of a nice gluing structure, some local structure, there is no canonical choice.
But I thought the canonical two framing is what matches with the Reshtikin-derived partition function. Doesn't that obey
it is the partition function, but TKFT, if you want to define Reshtikin-derived TKFT, you cannot define it's a pure TKFT. You can only define as a TKFT on the category of Bardisms with this P1 structure. If you want, there is a way to define Reshtikin-derived invariant on a closed three manifold. Yes, there is a canonical choice of kind of framing. But if you want to have a TKFT structure with respect to what we're doing, then it only makes sense to define as a the function on the Bardisms with P1 structure.
I see. I didn't know that. I see.
So if
you
want to have some locality property, then there is no. Then we have to consider this choice of framing, and we do want to do that.
I see. And here in your story, you also want to preserve the locality of the defect, and therefore you don't want to. And therefore, there's no canonical two frame.
If I just consider like three manifold, like defect on a closed three manifold, then I probably yes, there is some canonical choice. But if I want to consider some sort of cutting gluing defects, then this canonical choice is not going to be kind of respected by this operation.
I see. Thank you. That's very.
There are some mathematical papers which actually define kind of. But there is one choice is to choose a P1 structure, and the other choice is to choose what is called signature structure, which is a bit weaker condition, which kind of you want to extend your kind of three manifolds to 4 dimensions, to some kind of you essentially consider your 3-dimensional series as the boundary of some 4-dimensional TKFT.
Okay, thank you.
Yeah, this is a subtle choice, but it's important. Thanks for the question. Any other questions? Okay. So if you want to get rid of this dependence on framing, one way to do this is to put on top of the defect Reshtikin-derived type of TKFT. So we can consider Reshtikin-derived type TKFT, which is associated to a 2-dimensional rational conformal field theory with a certain central charge. So there is a kind of general construction where kind of the primaries of rational conformal field theory correspond to line operators and so on. So it's a kind of in more mathematical words, the 2D rational conformal field theory gives what is known as the structure of model tensor category, and by model tensor category, you can construct Witten Reshtikin-derived type TKFT. So if you take a rational CFT, this CFT has some rational central charge, and as was already argued by Witten in his paper about Jones polynomial and quantum field theory, the partition function, if you change the framing, the partition function of TKFT changes the phase as follows. So the change of phase is also proportional to F. So by appropriately choosing our C, we can cancel out the dependence on framing. So we will stack this TKFT, 3D TKFT with our defect. And so finally, we can consider the following family of defects labeled by pairs of central charge, C, some rational number, and T is a TKFT which is constructed from a rational conformal field theory with a corresponding central charge. And so the defect is defined as follows. So it's what we had previously, with alpha basically replaced by 2 pi C divided by K times the partition function of my TKFT on Y. So this is how our central charge is related to the original angle alpha. So in principle, so let me note that for general alpha, for general rational alpha, such TKFT exists. So, for example, if we consider alpha to be some 2 pi of the form 2 pi p divided by n, where p and some integers, some positive integers, you can always realize this t to be a stack of some number of copies of SU2 Chern-Simons series. So we can easily calculate the central charge by using the Sugar-Wire formula to get the following expression. And indeed, we get an agreement with this condition. So in principle, if one wants, one can always deal just with stacks of SU2 Chern-Simons here, but it's not necessary. And so let me note that such pairs labeling our defects, they form a monoid, commutative monoid structure. So let me remind you, the monoid is almost the same as a group, but there are no inverses. And the monoidal operation, so the operation in the monoid is the following. So we just add up. It's just basically correspond to stacking the TKFTs and the corresponding addition of the central charges. And so this monoid structure corresponds to a fusion of the operators that we consider, the topological operators which we just constructed in the following ways. So if you fuse two operators, the corresponding labels, so they are labeled by elements of the monoid, those corresponding labels just add up according to the monoid law. And so this monoid, so it's a kind of huge monoid, but it's related in some simple way to Q-mod Z symmetry, which can be understood as a subgroup of the original U1 symmetry. In a way that they can be said to be related by a surjective morphism of monoids. So a pair CT is mapped to the angle alpha, which is just C divided by K. K, I remind you, it was our parameter, which is the anomaly coefficient. Okay, so any questions at this point? Okay, so now let me a bit complicate things and consider a more general case of non-trivial background U1. So moreover, if I consider the case when the fermion parity is contained in this U1 global symmetry, we can drop assumptions that the alpha manifold is spin, because then we can, again, in this case, we can consider U1 as a part of the spin C structure. And we know that although not every manifold admits a spin structure, every manifold admits a spin C structure. And so when we turn on non-trivial background U1, we have this more general expression for the divergence of the current. And so if we take just our operators that we just consider it and consider the deformation, again, we deform y to y prime, the ratio now will be not zero because of this extra term proportional to C1 squared, which is the same as F squared up to a constant. So we have to deal with this, but yeah, this can be done essentially in the same way as was done in these papers, but with the difference that here the U1 is not gauged, it's just a background U1. And this can be realized, so explicitly this can be realized as follows. So so we can do this by stacking on top of our defect that we constructed this far, an extra abelian TKFT, which is coupled to this ambient U1 gauge field. And such an abelian TKFT can also be realized as a certain abelian Chern-Simons theory, which can be described by a choice of certain rank L integral lattice, so that if you choose a particular basis in this lattice, the Chern-Simons level matrix will be given by the inner product of those basis elements. And then kind of in this setup, we can describe coupling to the external U1 gauge field by choosing an element of the dual lattice M, so that kind of the path integral of this three-dimensional abelian Chern-Simons theory on Y coupled to external U1 gauge field A is written as follows. So it's we consider path integral over L U1 gauge fields. So this is a standard. First, we have a standard abelian Chern-Simons term, and then we have a term which is corresponds to coupling to the external gauge field, which is described. And again, if you choose some particular basis in the lattice, it's described in terms of these integers and i's. Okay. And so we add. So what we will do, we'll add on top of our defect, we add this extra abelian TKFT, which is now coupled to now non-trivial background U1 gauge field A. And now they are they will be labeled by the quadruples CT, and also which we had before, and lambda and n. And so in order to cancel this anomaly of our symmetry, we need to choose our n lattice so that n satisfies a particular condition of the following. So the square of n in the lattice basically this part. So if you integrate, this Marley can be understood as follows. So if you integrate out the small a's and use this property of small n, we get that this will exactly cancel out this type of this term. And but now, since so in general, if this signature, if this lattice has non-trivial signature, we have to adjust the we actually have to adjust the TKFT which we chose before, because it will contribute. This new TKFT will contribute to the center, to the framing anomaly, to the central charge. And so now our TKFT which we chose before actually has to have a central charge C minus signature of lambda. But of course, there is some sort of ambiguity of choosing this because we have a pair of TKFT, so we can this T TKFT which we had before, it can contain a part of this abelian TKFT which is not coupled to any way to the background U1 gauge field. So there is certain, these kind of quadruples have the following equivalence relation, which basically corresponds to kind of transferring a part of abelian TKFT corresponding to lattice lambda prime to our TKFT T. And this is a part. Corresponding to lambda prime. It has a trivial coupling to the background gauge field A. And for this more complicated case, we still have a monoid structure. So now we consider monoid to be as a set of equivalence classes of these quadruples labeled by a central charge C, some TKFT or Hessian-derived type T, lattice lambda, and n element of the dual lattice modular equivalence relation, which we had before. And again, we can define the following binary operation where we stack our TKFT together, add up lattices, and also add up these elements in the dual lattices, which describe the coupling to the ambient U1 gauge field. And so again, this monoid binary operation will be in agreement with the fusion of our non-invertible defects. And again, so this monoid has a surjective morphism to Q mod Z subgroup of original U1 symmetry by the following map. So the original angle alpha is related to the central charge in the following way.
Sorry, I missed it. What was the equivalence relation?
Yeah, the equivalence relation is the following. So yeah, we consider it could happen that the lattice has a part which for which this n, because the component of n is trivial. So it means that this part corresponds to kind of abelian kind of decoupled abelian TKFT, which doesn't couple in any way to the ground gauge field, and we can kind of put this part. We can transfer this part into this TKFT T, which we had before. This is just kind of shuffling between these two series which we have here.
Okay, yeah.
Yeah, so in principle, yeah, so there's some way to describe this more invariantly, not in terms of lattices, but in terms of the corresponding discriminant groups. But let me not to go. But there is some subtleties, but let me not go into this. Okay. So yeah, so I'm basically done with the case of U1 symmetry. Are there any questions at this point? Okay, so let me then proceed with the case of Z4, when we have a Z4 global symmetry which contains fermion parity, again in 4 dimensions. So the choice of background Z4 then corresponds to choosing a spin times Z4 structure where we divide by a diagonal Z2 on our space manifold. And the anomalies in 4 dimensions are known to be classified by this Pantragian dual to the corresponding 5-dimensional Bardism group, which is known to be Z16. So to kind of fix anomaly coefficient, we choose this number nu modulo 16. And so instead of the kind of anomaly polynomial, now we have a certain invertible 5-dimensional TKFT, which has action which can be written in this form. So let me explain what this means. So first, if you have a spin times Z4 divided by Z2 structure, we can produce from this structure a Z2 gauge field, or equivalently the first kind of the class in the first cohomology with Z2 coefficients, corresponding to this quotient map where we kind of quotient, we forget about spin and we quotient Z4 with respect to this Z2. And now it is known that so we can consider a class in homology Poincare dual to this A in our 5 manifold, and it is known that it always can be represented by a smooth, possibly so in general unoriented 4 manifold inside this 4 dimension inside 5 dimensions, and moreover, this 4 manifold has a naturally induced spin plus structure from the spin times Z4 structure by what is called Smith map. which is a kind of generalization of the original Smith map considered by these people, Hayson, Margotsky, and Sorgnerin. So now, and so what we mean by this PD of A is a corresponding pin plus manifold, and then eta is the eta invariant of this pin plus 4 manifold, which we normalize for convenience. We normalize it so that it's integer valued and defined modulo 16 on closed pin plus 4 manifolds. So how can I kind of geometrically can understand what's happening? So we have some 4-dimensional theory which we have anomalous the Z4 symmetry, and so we understand the anomaly in terms of the inflow, and this means the following. So we also have spin times Z4 structure in 4 dimensions, so we can consider A kind of the corresponding A Z2 gauge field produced by the structure in 4 dimensions. And we have a Poincare dual to this A inside 4 dimensions. So what we need to do, we need to extend this to some sort of 4 manifold, this 3 manifold, to a 4 manifold in 5 in the bulk, 5-dimensional bulk, and we need to put on top of this 4 manifold this kind of action, which is just so the total 5D action can be written this way, but this can be also just putting a eta invariant type effective action on this Poincare dual. Okay, so let's see what is the charge. What is it? Kind of, how do you understand charge operators here? So consider kind of a network of kind of naive or classical Z4 charge operators. So as usual, we want them so they can form a certain. In this case, actually, to get something kind of non-trivial, interesting, we want to consider a non-trivial kind of a general network of charge operators, and such networks can be encoded kind of in terms of the choice of the chain. Sorry, 3 cycle, actually 3 cycle inside our 4 dimensions with Z4 coefficients. So the kind of the coefficient of our so in the cells of our chain, they correspond to kind of local charges of our operator. So one can imagine a picture like this schematically. And moreover, so we have only 3 non-trivial charges for Z4, like -1, 2, and 1. But since the change of orientation of the defect corresponds to a change of the kind of change of the sign of the charge, we can actually assume that they're only in the networks. We only have operators of charge 2 and charge 1. But with a particular, if you adjust the orientations of this, if you swap, we can swap orientation of all operators of charge -1, so they all become operators of charge 1. So when we have a network which of charge operators which looks something like this. So what does it mean that we insert such operator? So insertion of such operator means that we change our spin times Z4 structure by the corresponding element of the first cohomology with Z4 coefficients. So in general, this kind of these structures. So what we know that the space of these structures, they form what is called torsor over this first cohomology group. Okay, the two different structures, they differ by element of them. So what we're going to talk about changes of structures, if you want to have something defined in terms of the cohomology classes. And yeah, so this and the relation to this first yes, to the first cohomology class is given by Poincare duality. So kind of we take so our y tilde, which was a 3 cycle with Z4 coefficients, so it represents some class in the third homology. We consider this Poincare dual, which is the first class in the first cohomology with Z4 coefficients. And so in the insertion, so the insertion of such defect changes our structure, spin times Z4 divided by Z2 structure, in the way that if you consider y kind of is a mod 2 cycle, which is obtained by mod 2 reduction of our cycle with the 4 coefficients. So here it's this mod 2 reduction is visualized in blue. So the y tilde was the kind of the full with the full network of defects, and y is this its mod 2 reduction. So yeah, so the insertion of such defect, it changes our spin times Z4 structure in the way that it modifies our this Poincare dual to A, the Z2 field, which you considered before, by the union with Y. And therefore, since before we had to extend, due to anomaly, we had to extend this Poincare dual of A to kind of to a hypersurface in 5D bulk and put it on top of it some trivial effective function. We have to do the same with Y when we insert this defect. We have to also extend our Y into the 5D bulk, so that this extension supports this action, which is a proportional to ET invariant. Okay, and in a similar way, kind of we can kind of so here we don't get a because of this we don't get a kind of purely like well-defined topological defects in 4 dimensions, because we need to choose the extension, which is again there is in general there is no canonical way how do you extend it first in the bulk, but this can be cured in the following way. So we can consider a 3-dimensional. Sorry, this should be a pin plus, not pin minus. Typo. Pin plus TKFT, 3-dimensional TKFT, which has anomaly described by the 4-dimensional invertible TKFT, which has an action, 4-dimensional effective action, also proportional to the ET invariant, but with opposite sign. And so we know that the anomalies of 3-dimensional series with pin plus structures, they're classified by this Pendragon dual to the 4-dimensional pin plus Bordizon group, and which is also Z16. And the TKFTs which realize such anomalies, they were considered by various people listed here. And yeah, so yeah, there are various kind of ways to explicitly realize them, which I'm not gonna talk about due to constrained time. And so what we can do, we can again stack our kind of naive charge operators with these with such a 3D TKFTs, where we only actually need to stack them on this kind of on the part, put them on top of the part of this defect network, which was mod 2 reduction of the full chain with the full cycle with the 4 coefficients, because we only need to extend this kind of the mod 2 reduction part, which is shown in blue here. And so since we can choose kind of to get an ambiguously defined this partition function of this TKFT, so the TKFT on Y, we also need to choose some extension to some 4-dimensional manifold Z, let's say Z, which we can kind of for simplicity we can kind of imagine that it's embedded in a 5. We can choose it to be embedded in the this 5D bulk, and but together this kind of the dependence on these extensions it cancels out, because they have a kind of yeah, the action here and here has opposite signs. So now one way to kind of visualize this is that we can kind of combine these two extensions, this kind of a pair of 4-dimensional hypersurfaces in 5D together, and we kind of smooth them out here a little bit, and we push them into the bulk. So we push it away in the bulk, so that actually this becomes a well-defined defect in 4D without need of choosing any extension. And of course, since again this TKFT which we edit is has to be non-invertible, we get kind of so we cured one problem, but we earned non-invertibility. Okay, any questions? Okay, let me briefly mention how this is relevant to the standard model. So in standard model, we consider the case where the number of what is called sterile Ryan-Haidt neutrino is not equal to the number of flavors. So physically observed number of flavors is 3, but we can kind of consider it more general if you want. And so then what happens is the following. So for example, there is for the case of U1 symmetry, which contains fermion parity, we can consider the B minus L symmetry. The symmetry corresponding to B minus L charge, where B is a baryon number and L is a lepton number. Well, in order to be, so in place of this charge, if you consider like fundamental particle, like quarks, this charge is not integer quantized. So to get an integer quantized, we actually have to multiply it by NC, the number of colors, which we assume that it's 3. And then this symmetry will be, will have anomalies as before of this type, where K is equal by this number and L is equal by this number. And similarly, we can also consider Z4 symmetry, which also contains fermion parity as a certain combination, kind of as a Z4 symmetry, which corresponds to a mod 4 reduction of a certain combination of charges, where B and L are as before, baryon lepton number, and Y is a hypercharge. And then the anomaly coefficient is given again by this difference between the number of right-handed neutrinos and number of flavors modulo 16. Okay. Yeah, that's it. That's all I wanted to say. Thank you.
So thank you, Pavel, for such a nice talk. Are there questions?
Hi, Pavel. Thanks for the nice talk. I have a general question about such non-invertible symmetry from gravitational anomaly. So in the case without gravitational anomaly, like the story in QED that we consider, and also Clay and Cantor will consider, it was very important that there's a magnetic one-point symmetry. So one way to construct the non-invertible symmetries there can be the way you present it, but alternatively, one can also realize them by gauging a magnetic one-point symmetry. And relatedly, the dynamical monopole will break the non-invertible symmetry. Now, I wonder in the gravitational counterpart of this story, what would be the analog of the one-point symmetry?
Yeah, we thought about it, but we cannot find the direct analog.
Right.
Because yes, the thing is that here it was like, well, in that story there was something like this C1 square, which was important. That was kind of important fact for that approach. It was factorized in this way, but P1 is not factorized in any way, so we cannot represent it as a square of something. Only only maybe if you consider it's like with a special case when you consider like only P1 modulo 2, then it can be factorized in terms of the product of two product square of Stiefel-Whitney class, but again, we couldn't actually make quite a sense of it. Yeah, but again, yeah, the short answer there is at least we don't see a direct analog because there's no this factorization of P1 similar to this case. And yeah, and also we don't know analog of this non-invertible action on the extended line operator or the 't Hooft operators. We also don't see analog of this type of thing. But
yeah, I see. Thank you.
Other questions? Okay, so if not, let's thank Pavel again. And let's stop the recording.